So it's a real pleasure for me to be here, especially with Sir Gareth's family present in the audience, and kind of daunting for me as well, given the history of previous speakers that have given this particular lecture. So I hope I don't let them down with what I'm going to talk to you about today. It is quite a general lecture. I don't go into much in the way of technical detail, although on the nuclear parts I am perfectly willing to answer whatever questions you might have, but your own academics in the audience are probably better able than I am to answer some of the detailed questions on the other technologies. Yeah, picture of the famous man himself, and my recollection of Gareth was all the work that he did with respect to the policy associated with increasing the numbers of science and technologists in the pipeline in the UK, and to increasing the remuneration available to postgraduate students who still benefit from that today. But also, as part of my career, I did a spell on the Council for Science and Technology. Gareth had been on a precursor of that, but the work that we were involved in was the development of plastic electronics associated with the Centre for Process Innovation down at Sedgefield. You know, a lot of it based on Gareth's early work. So a great man, and somebody who's made a big impact in the UK science and engineering landscape. So what I want to do is run through the low carbon energy environment, look at how we're progressing, because if you look at the media and both print and broadcast, you might think we're doing quite well, and there are quite a lot of issues associated with most of the forms of low carbon energy. So if we go back to last November, the UN Climate Change Conference, where there was a lot of hope and expectation with the nations coming together with us as hosts in partnership with Italy to try and persuade the key decision makers to do the right thing. But for many climate activists, Greta Thunberg summed it up after the 2-week summit, which was a Global North greenwash festival, because she was particularly concerned about the lack of commitment to really row back on the use of fossil fuels and to do more to mitigate against climate change. And if you look at the world's top emitters responsible for over 60% of the global emissions, it's not surprising that they're China, Russia, India, the USA, but particularly China and the USA. And we're an only tiny part of the overall equation. You know, similar to Italy, Turkey, Poland, we're all about 1%, as are most of the countries on the top of the pie chart there. So although we only make a tiny contribution, we're a first world nation. We're not a third world nation. And so, you know, we're morally obligated to do our bit to try and reduce our emissions, as well as persuade the big guys that they need to do a heck of a lot better. So if you look at contrasting access to energy globally, you know, in India, you know, many families are still lucky to have what's on the picture, whereas we in the West are able to have, you know, a multiplicity of TVs of various sorts and every 21st century asset that you could envisage. But in today's environment, compared with, say, 40 or 50 years ago, where you could do without power occasionally, in today's environment, we need it for transport, we need it for cooking and for space heating in our homes, we need it to make sure the lights and the power stays on if we're in hospital for an operation, and we need it to be able to Zoom our granny. So you can't, it's more difficult to do without it now than it was 50 years ago. Because we rely so much on IT and AI systems to keep our lives running, to charge our phones, etc., etc. So we can't do without power down the wires. And in terms of what creates our carbon footprint, it's not just electricity, it's transport, it's business and residential means, particularly the space heating for those and the heat used in industrial processes, agriculture, waste management, and a little bit in what's called other, which picks up a multiplicity of things. If we look at the impact of COVID, what's really stark is if the big nations who currently pollute aren't running, then the pollution goes away. And so these were shots from NASA back in January 2020 to show the difference between a fully functioning China and a not very functioning China due to shutdown associated with COVID. But then it shut down an awful lot of our normal lives as well. So we've got to do something which creates the same effect as COVID, but without the disease itself. So if you look at demand for energy, this is energy, not electricity, from 1995 through to 2020, you'll see that we've made some significant changes. We've made some significant reductions. But you will also see that, if I can just work the pointer, you'll also see that most of our problem is caused by the fossil fuels of natural gas, petroleum and coal. And although we've done a lot to add wind and solar and hydro, it's still a tiny amount in the overall scheme of things. Bioenergy and energy created from waste is a bigger proportion. Nuclear stayed pretty stable throughout that period. But the dip at the end there is due to the impact of COVID. And we're actually back up at pretty much what we were pre-COVID times. In COVID, you can see what happened. Pretty much everything reduced, particularly transport. The only thing that went up was domestic, where we were at home more often and therefore we used the space heating and cooking, etc. a lot more. In terms of transport generally, diesel, petrol, everything tanked and aviation tanked back in 2020, but they're all back up now at similar levels to what they were before COVID struck. So if we look at electricity consumption by sector, what you'll see at the bottom there is industrial consumption down by 20% over the 20-year period. But, and so you'd think, oh, that's great, industry's being more efficient. Well, actually, maybe it's not so great, because what we did was offshore a lot of our heavy industry to places like China, where emissions have gone up. So we've got to be careful what we draw out of the statistics. It's not that we're doing very well in terms of efficiency and demand reduction, it's that we've offshored a lot of what we actually need. In terms of electricity generation over that period, what you will see is that there was a big increase in bioenergy at the top there. The hydro and the solar, small increases, fair increase in wind, nuclear pretty static, and the big loser in all of that, coal, in terms of what we have available to us. Now, the Committee on Climate Change had a blueprint for a fully decarbonised UK, a rich depiction of choices for reaching the goal of net zero. Well, you know, would that were true and followed? Their previous report had said that the policy instruments weren't even going to enable us to meet the 80% reduction by 2050. So although there are a rich depiction of choices, our policy and our means of interacting and our means of implementing them are nowhere near getting us towards that goal. So in terms of low carbon energy, you've basically got earth, air, fire, water and sun. And that translates to nuclear, biomass, hydro, marine, solar and wind turbines. And I guess there would also be geothermal, but I haven't actually put that on the slide. But in terms of the carbon contribution to the major source of electricity, what might surprise you is how low nuclear is compared with some of the other sources. Nuclear and wind are not that different, and that counts for all the input to making them viable sources. So it includes, in nuclear's case, mining, waste management, decommissioning, and all that sort of thing. Most of the carbon footprint for both nuclear and wind is in the concrete that you use to actually build the stations or the wind farms. So you'll see that biomass, although people think it's clean, actually isn't. It's a significant contributor to our carbon output. So where does our electricity come from? Now, I'm passionate about this app. You can get it on your phone. It's called Electricity Map. It's an open source. There are other sources that do the same thing, but this one is particularly graphic in what it does. And you can point to a country and it will tell you where the electricity is coming from. So France, the reason it's green is because it's nearly all nuclear. Sweden's 50-50, nuclear and hydro. Norway's pretty much hydro. We go anywhere between sort of brownish there to a slightly lighter shade of brown, depending on how much wind is on the grid. And so this was the picture on the 11th of January, sort of just a couple of months ago. And what I want to really show you there is what Germany was doing. Because people normally perceive Germany as a very clean and green country. But in fact, the only thing that's keeping the lights on in Germany when the wind is low is coal. And Germany has just increased its strategic stocks of coal massively in order to compensate for the fact that its other source is gas. And I'll come back to the geopolitics of gas in a minute. Okay, so Great Britain on the same day, our go-to is gas if there's not a lot of wind or solar on the grid. And I just want you to remember this here. This is the capacity that's installed in the UK at the moment, but you don't get what you've built all the time. If the wind doesn't blow, then it can be way down. And similarly, there's a large excess of gas capacity because we need it in case we need to switch it on. Okay, so gas geopolitics. I've put this in as a result of the things that are happening in the Ukraine at the moment. Where do we get our gas from? Well, we're no longer masters of our own universe here. Less than half of our gas is actually ours anymore. We get a lot from pipeline from Europe, a fair bit from Norway, which is good. But anything that comes through Belgium or the Netherlands is subject to the same stresses as the rest of Europe. It's got a big Russian connection associated with it. And of our LNG imports, this is where we get our LNG imports. Qatar, nearly 50%. The US, just under 30%. Russia, 11%, although our Prime Minister said that we didn't want to get stuff from Russia, and so that will wind down this year. But there's still a problem, because we have hardly any gas storage capacity compared with everybody else. We're really low on gas storage capacity. And there's been lots of articles in the press over the last year about that. You'll see from the graph here, we're right at the bottom. Right? Italy, that's got a similar population to us, has a massive amount of gas storage capacity compared with our weedy amount down at the bottom. We've just never thought about it strategically as being important. And right now, it's really important. Just out of interest, you've probably heard this on the news anyway, 40% of the European Union's gas comes from Russia, and 30% of its oil comes from Russia. So these are big strategic issues for countries right now. Here in the UK, we've an issue that most of the rest of Europe doesn't have, because we've got low interconnection electricity-wise with the rest of the mainland Europe. Most of the rest of mainland Europe is much better interconnected. Now, I showed this graph. It's a 2006 graph, but I wanted you to note the capacity at the top. That's what we used to use. Around about 60 gigawatts was required to keep us on. There's a massive peak happens in winter as people come home from work and as people get up in the morning. And you've got to be able to manage those peaks. You've got to be able to deliver what you need at the time you need it live. So there's a lot more needed in winter than there is in summer. Right now, I took this one earlier this week from the electricity map. This is what our profile looked like. Lots of gas on the grid, not a lot of solar. Wind was variable, because if wind is available, they'll take it. So if there'd been that much wind, then it would have been on the grid. Okay. What they do is they use gas to make up the difference. If wind's on, then we have it. If it isn't, we don't. But we're still burning coal if we're a bit tight on supply. And we've got to have a responsive system to cope with this in the afternoon, or this in the evening, and this in the morning rather. It's got to be available when we need it. So if there isn't any wind, we've got to have something else that will actually keep our lights on. So we need low carbon energy supplies, but we're aiming to electrify our transport network and to electrify our homes. And that means that we're going to actually double or treble our requirements for electricity on the grid, which is already not clean. So it's a big, big challenge if we're going to achieve what's required in reduction in transport, reduction in space heating, and yet keep the lights on. Now, over 10 years ago now, I was lucky enough to be part of a study by the Royal Academy of Engineering that said what we're going to need for 2050 to meet 80% reduction in our emissions. So we suspended belief about whether we believed it was doable or not at the time and said, what do you have to build with no restrictions, no financial restrictions? What can you build? And so this was the sort of thing that we had to do. It was build over 9,000 big turbines onshore, the equivalent of 38 London arrays of offshore wind, solar voltaics. You can read the figures yourselves, but wave machines, tidal stream, etc. And you'd still need 80 big power plants, either nuclear or fossil with carbon capture and sequestration, and you'd have to reduce demand in order to meet those levels. So that's what it said. 9,600 of these, build loads like that. That's the Walney wind farm. You guys are probably more familiar with the Hornsey wind farms off the east coast. But they're massive wind farms, 245 square kilometres, the London array. 73 square kilometres, the Walney wind farm. Pelamis wave machines, that's the equivalent of building 3 miles a month for the next 40 years. So it's a London tube train a day of wave machines. Pelamis actually ceased to exist after we wrote the report. And although there has been some progress with wave power, it's still not commercially available. Marine turbines, closer to commercial realisation, but with still quite a lot of issues to go before you see them large scale. The Severn barrage would have been a good thing to do, but that's already been curtailed, mainly on environmental grounds and cost grounds. So at the moment, there's no sign that the Severn barrage would go ahead. Lots more solar panels, either in fields or on houses. So basically, everything possible and as much of it as possible, and also think about reducing demand. So all technologies, no preferences. I've got no particular preference for nuclear in this sense. It's what can we build that's green that's going to help us. So this is what we'd said that ought to be built down this column. So that's what you need to build, and that's what it actually gives you. So it shows you the difference between what you build and what you can actually get power-wise out of it. To be fair, some of the offshore wind efficiencies have increased quite a bit, so that figure would be bigger. But you'll see that we haven't built anything like as much as we would need just to meet the 80% by 2050, never mind about the 100%. So we haven't built enough onshore or offshore wind. We haven't put as much solar panels in fields or on houses as we could and should have. And only small local schemes of hydro have been built. And we haven't built any new nuclear power stations or fossil stations with carbon capture and sequestration that are commercially available. So we're not doing too well on the what do you have to build to do it yet. So demand reduction required across the whole economy without sacrificing industrial competence and availability, and make sure we build lots of everything in order to meet those targets. So is the answer coupling renewables with battery storage? And certainly in South Australia, that's the sort of initiatives they've taken to try and get some way towards that. But there are issues with batteries, both old and new. The only batteries that are actually recycled at the moment are your old-fashioned car lead-acid batteries. There haven't been major steps taken yet, although there are some underway to actually recycle the batteries that we use in our electric vehicles or in our static systems or in our home power walls. So we've got to do a lot more with the sustainability of batteries as well as making them available. So in terms of how we're doing with cars, well, although there's a lot of noise about it, only 7% of new cars sold in 2020 were electric. There were some more that were hybrid, but pure electric cars, only 7%. Petrol was still the most popular fuel type, with over 55%, with diesel just slightly behind. So, our commitment is not yet there, both as procurers and with the infrastructure that's needed to go with them. Because there's a charging point challenge. Like mobile phones, the charging points are all different. If you drive a Tesla, you're probably okay because they seem to have got their infrastructure a lot better than the others. But, if you've got a Nissan Leaf, you might be driving around trying to find somewhere where you can actually charge the thing up that's working. So a lot more infrastructure thought required about how we manage the charging point challenge, both domestically and out on the open road. The other thing about batteries is about the technology associated with them. Much of the global supply of lithium comes from the Atacama Desert in Chile. And so there's big questions about whether that is sustainable long-term or not. And certainly if you talk to the average punter in Chile, they aren't too happy about having their entire lithium supplies and the environmental impact on their desert areas affected by mining companies that drain them. Similarly, cobalt, the other key source in batteries. Cobalt mining, much of the world's supply comes from the Democratic Republic of Congo, and it's not exactly people-friendly, never mind about environmentally friendly in the way in which it's extracted. So we need to think about the sustainability as well as the availability of the things that we need to make our 21st century society work. Okay, so the challenge for batteries, they need to be optimized for better performance, so longer life, faster charge, safer, more resilient to environmental stresses. They need to be cheaper and mass producible, and they need to be increasingly sustainable and recyclable. So different materials that are abundant, not ones that are in short supply globally, and fit for purpose. So meeting many demands as well as just cars and static systems. So, stationary storage, yes, to grow the renewables percentage in the energy mix, but all the other criteria have to be satisfied as well. So what about hydrogen as an alternative to gas central heating and as a better energy vector for transport? Now, in the northwest, there's a project called HyNet underway, which is a hydrogen energy and carbon capture system, which is putting 20% hydrogen into the normal gas mix for the punters that use it. And that's going quite successfully. And I understand that there's a similar initiative underway here in the northeast. But one of the questions with hydrogen is how practical is it to put it in the main high-pressure gas network? And there is still a lot of work to do to make sure that is possible and the right thing to do. Because hydrogen embrittles some of the materials that are used to construct the high-pressure gas network, and it's also a very, very leaky gas. If there are leaks in the pipeline, then it's obviously not going to be an ideal solution. So lots of work to do on that. For transport, University of Birmingham's Centre for Railway Research has got trains running now that are running on a combination of hydrogen fuel cells and lithium-ion batteries. So it's a combination of the two that make it possible for some rail transport. Studies have been done about other things that can help the sustainability of liquid biofuels by the Royal Academy of Engineering, which you can get from their website. Transitioning to hydrogen, some good work done by the Institute of Engineering and Technology, and a joint report from the Royal Society and the Royal Academy of Engineering about greenhouse gas removal, so removing it from the air, carbon dioxide capture. These reports are all available and can be studied if you want to delve into them. Similarly, the potentials and limitations of using CO2 for all sorts of other things, options for producing low-carbon hydrogen at scale. Ammonia might be a better vector than hydrogen alone, and making synthetic fuel for transport, particularly aviation transport, where there's quite a lot of research underway now. So are heat pumps the answer for domestic heating? There's quite a lot of publicity about, replace your gas boiler with an air source heat pump. There are some wonderful homes that are purpose-built that do a really good job at showing you how it would work, but they're built from scratch. With massive insulation and efficiency in the building construction, as well as the installation of either air source or ground source heat pumps, solar panels, etc. Because this was true until last week, probably. To buy 1 unit of mains gas, you pay about 4 pence kilowatt hour, And if you use 1 unit of electricity, it'll cost you about 15 pence per kilowatt hour. So historically, gas was a heck of a lot cheaper than electricity per kilowatt hour. But with the crisis in Ukraine, the price of gas is screaming through the roof. And so the economics of heat pumps are getting closer to the economics of gas. But the issue with heat pumps, it's not just about the heat pump itself. If you like, that's the easy bit. What you have to have is a massively well-insulated home with underfloor heating, better insulation on all walls as well as roof, new radiators that are 2.5 times bigger than the regular ones in order to take advantage of the heat pump's abilities. So you either need a large surface area in your heating equipment or insulation that holds onto your home. So if we were building homes like they do in Sweden or the Nordic countries, then we might stand a chance. But our building industry is still lagging behind what is needed in terms of 21st century building technologies to take advantage of heat pump installations. And for already built urban areas like inner city Newcastle or Manchester or London or anywhere, houses that were built back in the 1900s all the way through to about 1990, trying to put heat pumps into that sort of environment is quite tricky from the point of view of taking advantage of what they can offer. Okay, so moving on to nuclear energy, my favourite topic, if you like. A major contributor to the UK's low-carbon electricity, but the really big question is for how long, and is it going to be upscaled? So I showed you earlier that nuclear energy is one of our lowest carbon forms of energy, but almost all of our existing stations close by the end of this decade. And unlike reactors internationally, we have to shut ours because the design that we chose way back when was of an advanced gas-cooled reactor design, and they have definitely reached the end of their lives. And we have to close them by the end of this decade. So the only one that will be left, apart from the new one that's being built in Somerset, is Sizewell B in Suffolk. All the others will have gone. So we have to replace that clean energy with something else unless we build new power stations to go with it. So why is it such a challenge? And it's because you need vast amounts of cash before you get power. It's about the money, not about the technology. And I'll explain why in a minute. Okay, for a pressurized water reactor, boiling water reactors are the same. Most of what you pay for your electricity is because of the financing and the capital that you need to build the thing in the first place. So most of the cost is in the capital that you borrow and its financing, unless you're borrowing at very, very cheap rates. The cost of the reactor itself and the operating and the decommissioning, etc., they're a minor part of the overall financial cost of electricity from a nuclear power station. And in terms of where does the cost come from, actually, you'd expect it to come from the reactor itself. Well, that's a small part of the overall money that you need for your reactor. The nuclear bit is actually not the expensive bit. The expensive bit is what you put around it in concrete and rebar, all the structure and the shielding, the project manager to do something complicated, and all the mechanical and electrical services. The turbines, etc., cost about as much as the reactor itself. And then there's the control systems and the project management that goes around it. So it's all about the concrete and everything else that goes around the reactor that adds to the cost. The very large construction sites for the big units, this is a shot from the American plant at Vogtle, and it shows you how big the construction site is at the time. But the reactor itself is only a small part, as you can see going in. You could fit, just having a look, 1, 2, 3. You could probably fit 6 1,000 megawatt reactor pressure vessels in this room. They're not very big. They're 5 meters in diameter, and they would each generate 1,000 megawatts of power. So it's a very energy dense sort of power system. Hinkley Point is one of the hardest of the modern reactors to construct. It's a design that was conceived in the 1980s, 1990s. It's got a large concrete base mat. It's very complex, congested, heavy, and the challenge in buildability is enormous. It's not very modular in its construction, which is why it's as expensive as it is, and because a lot of the construction has to take place on site. So these were shots earlier last year, in fact, of the construction site at Hinkley. So government at one point did have a strategy for nuclear. It was sort of to replace what we had, but it's just been really slow in actually implementing that. And so our original ambitions for new build were to build Hinkley Point, which is a French reactor, and do the same at Sizewell, which is still under discussion. We were going to build some American reactors, Westinghouse ones, at Moorside in Cumbria. We're going to build three of those. And we were going to build 2 Hitachi advanced boiling water reactors at Wilpher and Anglesey. The last 2 projects have fallen away because the companies concerned couldn't get the financing to actually make them go ahead. In Westinghouse's case, Toshiba had a meltdown, not a nuclear one, a financial one, and pulled away from nuclear. Hitachi, the Japanese thought, why the heck should we be financing the UK's energy with no commitment from the UK government, which is a fair point to take. So Hitachi still own the site at Wilpher and Anglesey and may well come back, but we'll see. So is the nuclear strategy in the shredder? Well, we thought that might have been the case until relatively recently, when great steps have been taken. So, just recapping from today, about 85% of our energy is fossil at the moment. Electricity is about 17% of that, and it's only about half decarbonised. And the Committee for Climate Change reckon we'll need 4 times as much electricity by 2050. I originally said it was between 2 and 3, but they say 4. But they also say that around 38% of that should be firm, as in not weather dependent. So not like wind or solar. We need stuff on the base load all the time to keep us going. And so around 10 gigawatts of green energy needs to be built each year between now and 2050 to meet that target. And we're nowhere near going at that pace. And all green technologies need to be deployed. Because if you look at where we stand with nuclear at the moment, if that's going back down to about 3%, and it's taken us 20 years to get this much of the wind and the solar and the hydro, you can see the sort of challenge that we've got in electricity generation ahead. I mean, one of the things I won't mention today is the fact that we've done nothing much about storage. Right? Our ability to store so that we can use electricity at a time when we need it, we're way off the pace in developing storage technologies. So what do we need to make nuclear investable if the government isn't going to pay for it? Well, we need the capital to be cheaper. We need to build lots so you get a factory environment. We need the financial risk to be mitigated before you start to generate. And we need a supply chain that can build the things. So use fewer bits, take less time, build lots, borrow the money cheap. It's not rocket science, but government hasn't necessarily woken up to that yet. So incorporating the best practice from other sectors is what the nuclear industry has been doing for the last decade, really. So, pinching good ideas from construction, from shipping, from automotive, from aerospace, project management, factory build, the digital world, and many more. That's what's been happening. And one of the biggest changes has been design for modularisation. Whereas historically they've tried to backfit modularisation to a design, which is really hard to do, and you can't do a lot of it, to design for modularisation at the outset, like the Rolls-Royce team have done with their small modular reactor, is the way forward. Because not only is your nuclear vessels, etc., modularised so that you can build those in factory, the whole of the concrete infrastructure that goes with it is also built in factory and then shipped. And that's a key part for their design. it's born out of what you could do in shipbuilding. We built Queen Elizabeth-class aircraft carriers, and Cammell Laird at Birkenhead delivered what's called super modules, 15 of those fully outfitted. They're the bits in red. So basically, they built them on site with 25,000 metres plus of pipe work, 60,000 metres of electrical cabling for each one, all the systems, high voltage, low voltage, HVAC, communications control, fire detection and suppression, everything in the modules, working and tested before they were put back together as a ship. So, if you can do it in shipbuilding, you can do it in nuclear power plants as well. So the best of the light water reactor small modular reactors are these three. General Electric's Hitachi BWRX-300, where the Canadian utility OPG have just agreed to go ahead with this as their choice. NuScale's, these are much smaller. They're only 50 megawatts per module, but they build them in 6s or 12s. The United States are going ahead with this design, and we've chosen the Rolls-Royce led small modular reactor, which is about 400 megawatts, to actually build the UK's future plant, as well as possibly 2 or 3 of the traditional bigger ones. So Rolls-Royce's, it was considered revolutionary because it's factory fabricated, and you transport by road the modules to site and then put them together. And their concept was, and this is important for fusion plants as well as fission plants, it's not a nuclear reactor you're building, it's a power station that happens to have a nuclear reactor as the heat source. And so it's really important that everything else is built as an integrated modular system. So even though it's smaller, it's still not cheap at just under 1.8 billion, but it will deliver power at 35 to 50 pounds per megawatt hour, which is about the same as offshore wind. And it will take 4 years to build instead of 10 or 12. Uses standard fuel, standard light water reactor technology, so it's not complicated, it's just built differently. GE Hitachi's is very similar. It's just a shrunk down version of the safe boiling water reactor that they developed back in the 1990s. It's just a smaller version of it with most of the components already proven in existing reactors, which is why the Canadian utility has chosen it. And again, it's about the same price point as the Rolls-Royce system. And they reckon they're going to be able to build these in 3 years. So UK's ambition, reduced electricity, this is what it was. This was on the government's hit list. The decarbonisation targets, science and innovation, owning the technology, finance costs, reduce them, get control of the build rate. But this is for the birds. If anybody thinks you can reduce the price of electricity, forget it. You're not going to be able to. Not unless there's another means of financing. Not unless they take it out of general taxation rather than your electricity bill. Because the UK's infrastructure needs completely replacing. We're living on what was built in the 1950s, 60s and 70s. And so, if you think you're going to see cheap electricity prices, you're not. So of the more advanced technologies, these are non-LWR ones that may offer something else. These are just examples of ones that are viable from the main reactor vendors. This is from General Electric, so is this one. 100. This is a sodium-cooled fast reactor, high-temperature reactor. This is one that Bill Gates is paying for in the United States. It's called Natrium. It's a sodium-cooled reactor. They're doing it with a lot of GE technology. Westinghouse have got a lead-cooled fast reactor, and they're building some prototype micro-reactors as well. So the big guys are in there and innovating with next-generation technology. In our world, in the UK's advanced landscape, we have a company called Moltex that is working on what's called molten salt technology. Now, those of you who've looked at nuclear studies over the years, none of this is new, right? All the physics was done back in the 1950s and 60s, immediately after the Second World War. So whether it's a high-temperature reactor, a molten salt reactor, a boiling water reactor, you name it, the physics and the ideas were there in the 1950s and 60s. What's brought them nearer to commercial reality is much better understanding of the engineering that you need and the control systems and the materials that you need to construct. So that's a molten salt one. The benefit of that is the salt is hot, so you could use the heat as well as the electricity. This is X-Energy's high-temperature reactor. It's based on a project that was run in South Africa in collaboration with the UK for a high-temperature reactor system. And Urenco, that's the nuclear enrichment company in the UK, they've designed something called U-Battery. University of Manchester was very key to that. And their reactor is tiny. It's 2 megawatt electrical, 5 megawatt thermal, and it's designed for remote off-grid applications like the Northern Territories of Canada, or to co-locate with centres for data centres, which are very electricity hungry. We'll probably see these, but not on main screen grid applications. Okay, so what about everybody else? Well, the US DOE is pouring billions into upscaling its nuclear endeavours. This was President Biden announcing what his government intended to do, invest $9.5 billion in clean hydrogen technologies, and they're putting a big bet on the nuclear end of that, which I'll close out with. Similarly, President Macron set out a plan for the nuclear renaissance. This was on the 11th of February. So France rowing back from curtailing its nuclear to pouring a lot of investment into new nuclear power reactors. 6 initially, then a further 8, and continue to develop its own small modular reactor. I would hope Rolls-Royce could maybe sell them some before they get to develop their own properly. But since the Ukraine crisis, you can bet your life that there's going to be a lot more investment going in by the existing nuclear nations, and maybe more from those who don't currently have them. So that was fission. What about fusion? Well, there's been great steps forward in fusion as well, and this university knows well the journey to fusion and has played a very significant role in it through to the present day. And it doesn't matter whether it's a tokamak project or a laser-based project. So the tokamak project, UKAEA STEP project, which will move to build sometime shortly. They've just got to select a site where that will go based on the investment that's been made at Culham on MAST and on JET. First Light Fusion, a startup company that is based on the laser and gas gun route with Holrom technology. These are all really important projects to move fusion on the journey towards commercialisation. Still got a long way to go because a lot of the challenges are in materials and in engineering development rather than the physics of fusion per se. So the journey is how to make it cheap, commercially viable and available 24 hours a day, 7 days a week, 365 days a year. So this is a shot of the inside of JET where there was the fantastic news a couple of weeks ago of the plasma burn there, and also the changes in technology, the replacement of the wall robotically to the standard wall that will be an ITER project copycat, or rather materials like this will be used at ITER. And then a shot of the ITER inside at the moment, just to show you the scale and the engineering infrastructure that is enabling ITER. That's the International Tokamak Energy experiment at Cadarache in France to go ahead. This is billions of investment of European money that's gone into ITER. So basically, there's a plethora of both advanced fusion technologies and advanced fission technologies out there. What I've shown you with a very brief canter through are the ones that are viable. You will meet many startup companies or you will see many presentations that are PowerPoint presentations or other presentations that will tell you they've solved the world and they've got a better nuclear mousetrap, whether it's fission or fusion. But what they lack is the validation, the verification, and the engineering evidence that they've got any chance whatsoever of reaching commercial reality. And I always like to quote Herman Rickover, the admiral that led to the fission technology being viable as electricity production. He basically had a saying, and you can look this up on the web, that an academic reactor, it's cheap, it's easy to build, we've solved all the problems, you can get on with it now. And in reality, the practical power plant has got massive development problems that you never thought you'd have. It's late and it's over budget. And that's what he wrote all those years ago in the 1950s. And it's true of both fission and fusion plants. So, what do we need to make a nuclear energy plant deliver to the market? It's not just about the nuclear bit, it's about the power station. And you've got to have considered everything: construction, fuel supply, waste management, decommissioning, including waste management and decommissioning associated with fusion. It's got to have an extensive validation and verification base. It's got to be licensable. It's got to have a credible route to market. It's got to have sites. You need the sites to build the things, whether they be fission or fusion. And most of it's got to be built in a factory. So finally, does nuclear energy have some additional functionality that the other clean sources of energy don't have? What about coupling nuclear with heat or hydrogen? So this is about deep carbonisation. What else can we have beyond electricity generation? And nuclear stations can be used for co-location of battery storage, desalination, there's some available globally now, or direct air capture of carbon dioxide. EDF is working on that now. Waste heat from stations could be used for district heat because, there's 300 degrees C of waste heat comes out of a power station. It's normally just put into cooling water and shipped out. So other countries use nuclear district heat. They do in Switzerland without any problem and have done for decades. And for a net zero economy, we need to produce green hydrogen. The hydrogen we produce at the moment is not clean. It comes from steam reformation of methane, so there's carbon dioxide created in the process. It is not clean at all. So we have got to find a way to produce hydrogen cleanly, and that's by electrolysis or heat-assisted electrolysis, which will get you a bit more efficiency. So nuclear facilities can be used beyond electricity generation. So the government's got a hydrogen strategy, and it has said nuclear has a place. It's just that it's not put a lot of money behind it to help get it along the way. So the normal low-temperature electrolysis, all reactor types can do that. High temperature, and you start to get more efficiency. And right at the top, you get thermochemical water splitting with only advanced reactors. And that's probably what will make the difference. So nuclear-produced hydrogen would have low life cycle emissions, and EDF at Heysham are already looking at some developments to make hydrogen that way. And the Nuclear Industry Association's produced a hydrogen roadmap, which you can look at. Just Google NIA and it'll get you there. Okay, so the advantages are you still get stable electricity, but it's a clean source of energy, and you can get heat as well as primary output. You can make electrolysis cheaper, and if you go to the advanced reactors, the high temperature ones, they'll give you an even better efficiency. And it's comparable with fossil with CCS. Okay, so finally, can advanced nuclear technologies succeed? Well, climate change is a unique opportunity for this because they should be part of the solution with a new generation of commercially viable, small-scale reactors. The advanced technologies will have predictable construction times, and therefore the cost will be reduced. And if you've got reduced construction costs and a firm timeline, then the private sector will come and invest. Internationally, we have a fantastic chance in the UK. We've got some of the best technology in the advanced reactors for export markets. And nuclear technology will enable the sector to finally play in the same low-carbon space as wind. But we need some thought leadership from government and a bit of an assist to really get it going, because nobody wants to buy number one. They all want to buy, numbers usually 4, 5, 6, and 7. They want to see number one, and certainly number one, and probably number 2 and 3, built, running and successful. So market pull would come, but only if the government supports in a policy sense. So the government's 10-point industrial plan: build more offshore wind, get us low carbon hydrogen, give us advanced nuclear power, shift to zero many vehicles, and then a number of other things on their 10-point plan. But they don't consider it as a system. There's no national roadmap to outline the journey to 2050. It's all piecemeal, whether it's nuclear or wind or whatever. And it can't be. The roadmap is aspirational. It's not real. It doesn't tell us how we're going to hit those targets. There's an unrealistic view of the role of batteries, and they haven't done anything like as enough as they could to accelerate clean hydrogen that's affordable. So there's much to do. I'm not saying it's impossible, but the challenge ahead is absolutely enormous, and we've only got 20-odd years to do it, to get to 2050. Thank you for listening to me.